I just wanted to make a short video concerning resonance structures and may also help reinforce drawing. So, in general, when we're looking for resonance, what you want to look for, let's say we have this molecule, CH3O, CH, double bond CH2. You want to look for lone pairs next to a double or a triple bond. That's a key setup for resonance. And remember that when you draw arrows, the arrows must start from electrons. So for instance, I could not start it from this carbon because there are no electrons on that carbon. I can start it from this lone pair, or I can start it from this double bond electrons. Usually you start with the lone pair. So one main situation to look for is this, in which you would push electrons in, making a new bond here, which pushes these out and then out onto the atom. And when we draw resonance structures, we use the double-headed arrow. And with pushing these in, we now have a double bond here. One lone pair left here. Oops, sorry. A single bond here, and then an extra pair of electrons out here. In general, what may be helpful for you too when you're doing resonance structures is to draw out all of the bonds to hydrogens so that you make sure you don't violate the octet rule. So if I take this molecule and draw all those out, I have a CH3 group attached to an oxygen, double bonded to a carbon with the H off of it, and then single bonded to a carbon with two H's and a lone pair. Okay, and then this lone pair. So everything has the octet rule satisfied in both of in this structure. We have octets satisfied. Up here we have octets satisfied. And then we also want to make sure we calculate formal charge. So on this top structure, everything is neutral and matches our neutral bonding patterns. But down here, we will have formal charge on both the oxygen and carbon. And so the formal charge on oxygen has 6 electrons minus 1, 2, 3, 4, 5. This is the short way. It's plus 1. And the formal charge on this carbon has 4 valence electrons minus 1, 2, 3, 4, 5, which is minus 1. And so we have to draw them on the structures. And so when we're comparing resonance structures, we have resonance structure 1 and resonance structure 2. You could draw arrows to show how 1 converts to 2, and you can in turn draw arrows back the other direction to show how 2 converts back to 1. Okay. Let me just take this off for now and show so there's not confusion. This is the same structure twice. I'm just going to refer to this one. So when we talk about the stability of which resonance structure is favored, you want to go through the rules. 1, who has the most bonds. If we don't count the hydrogen bonds and we just count the main, we have 1, 2, 3, 4. 1, 2, 3, 4. So they both have the same number of bonds. Number 2, octets, which I already mentioned, both were satisfied. Number 3, no formal charge if you can, meaning one is favored. Okay, but let me just list the remaining part of Rule 3. No formal charge if you can, and if there is formal charge, you want the least charge separation. Meaning, if you look at your examples from the slides, you don't want something with a 2 minus and a 1 plus when the other one could just have 1 minus. Okay, so you don't want large numbers of charge. And then if you still are satisfying these, then the third one is you want the negative charge on the most electronegative element. And I'll just abbreviate it EN. Most electronegative element. And electronegativity in terms of the periodic table increases up and to the right. Okay, so we have carbon, nitrogen, oxygen. Electronegativity is increasing this direction. And then under nitrogen we have phosphorus, and it's increasing up. Okay, so we want to keep these rules in mind when we're evaluating resonance structures. Okay, so you'll have resonance when you have lone pairs next to double or triple bonds. And you'll also have resonance when you have, let's say, a nitrogen with two CH3 groups next to a carbon with a plus charge on it, and two more CH3 groups. Okay, remember that the nitrogen will have the lone pair to meet the octet, so you want to look for lone pairs next to either a plus charge or to something not having an octet. In which this carbon does not have an octet. For it to have a plus formal charge, it only has 3 bonds, and it does not have 4. So you can move this nitrogen lone pair in through resonance. Remember that you can only move electrons and not atoms. So we have to draw all the atoms still and add our double bond here. And then when we calculate formal charge, the nitrogen would end up having formal charge in this case. And so if you look at which one of these is major and you go through our list of rules, this one has 1, 2, 3, 4, 5 bonds. This one has 1, 2, 3, 4, 5, 6. So this is most stable because most bonds. Let me also relate resonance to a functional group that we have. So one of the ones we learned today was an amide. The amide functional group. So let's say again, I'm just going to start with a CH3 group, and you're attached to a carbonyl, so C double bond O, and then let's say H, and let's say CH3. And I'm just drawing the bonds out now because we're still early in the semester and make sure that we have everything accounted for. Okay, so if you have the amide functional group, and let's say this was on sapling, the first thing you want to do is fill the lone pairs. Okay, so remember that you don't add lone pairs on carbons, but you do on heteroatoms. So this oxygen, to have an octet, would need 1, 2, 3, 4 electrons, and then this nitrogen would need 1, 2 to have an octet. Okay. The amide bond can participate in resonance because it meets the first criteria that I talked about, which is a lone pair next to a double bond. So you can push these in, and you can push these out onto the atom itself, onto the oxygen. Everything else stays the same, and you can draw your framework of your molecule, which is all your single bonds. Right. And then with these electrons pushing in, this made a double bond here, and then this added a new lone pair here. If I take the time to calculate formal charge, I will see that this oxygen is minus and the nitrogen is positive. One check that you can do to make sure you drew the resonance structure correct is up here I had 0 formal charge. So down here the sum of my formal charges must also equal 0. So here are the 2 resonance structures of an amide functional group. And obviously this one will be favored because it has no formal charge, whereas this one does. And I also want to point out here that you can see resonance is a flow of electrons. Okay, 2 arrows are not pointing in towards each other. So if you look at some of the practice problems I uploaded, one of the examples says, what is wrong with this? Okay, so just taking these electrons and moving them here, which makes this. The question asks, what's wrong with this? Okay, it might look okay to make a double bond here, but again, I want to reinforce that you want to keep in mind where all the hydrogens are. And so this is a CH3 and a CH3. And so without drawing everything, if I just draw it like this, okay, and then I push electrons, you see that oxygen does not have an octet. It only has 6 electrons around it. But remember, you can have less than an octet and be fine. What makes this problem wrong is this methyl group. If I expand just on this part, I have a double bond to a C and 3 bonds to H. I violated the octet rule on carbon by having 10 electrons, which you cannot have. Okay, so this violates the octet rule. And this is what makes the problem incorrect. Okay, it's not the fact that this has an